All right. Which one would you recommend? A twisted pair cable or a fiber optic cable? Pardon? Okay. If there was a lot of data transfer, and the reason?
More bandwidth.
Greater bandwidth. Right. No, data doesn't matter. What do you think? Give us another reason why you might recommend either one of them.
Depending on the conditions of the terrain, or
okay.
We need to put it through water. Okay, that would be fiber optic cable.
No, let's say there was no water, but it's difficult terrain, like mountains. Which one would you go through?
Then satellite.
Okay, so neither of the cables, right? The question was which one twisted. That's fine. Okay, next, give me another reason why you might go for one, prefer one over the other. Twisted pair and fiber optic.
Twisted pair is not fragile.
Okay, where the other one is a lot more solid. Okay, give me another reason. Think of something.
We go for the optical cable if I need a lot of band.
Okay, somebody's already, said if a huge amount of data.
And then the capacitor is big.
Give me another one, or can I come back to you?
Fiber optic cables are safer.
They're what?
Safer.
Safer. Why are they safer?
I forgot the name.
They're more secure, you're right,
Yeah.
but give me the reason, give me a couple of reasons why they're more secure.
They're not affected by something like
Electromagnetic noise. That's noise from a noise point of view, but that's not security. That's just to give you a clearer signal. Why are they more secure? Fiber optic cables. They cannot easily be tapped. Any other reason? Why are fiber optics more secure than twisted pair?
Because they don't have a signal in the sector. There's no magnetic signal or signals.
They don't radiate like twisted pair. They don't radiate electromagnetic waves or signals or energy that can be picked up by others. Right, and what's the problem with fiber optic cables? What's the disadvantage of fiber optic cables?
They can be quite brittle.
They can be brittle, yeah?
If we deal in tight spaces,
They cannot be twisted sharply. Any other problems with them?
Depending on if they're more expensive.
They can be more expensive, though that's debatable, but yeah, they can be. Any other?
I think if the distance is too long, you might need to repeaters.
We have to put more repeaters with twisted pair as well. So, in fact, what's the distance for repeaters in twisted pair or fiber optic?
100 meters.
100 meters for fiber optic cables. Twisted pair, yeah. Thank you. I was just trying to see it. And what about fiber optic? What? Fiber optic cables, 200 meters, maybe more? Anybody? Kilometers. It goes up to 60 to 100 kilometers. So there's a huge difference. Whoever was talking about repeaters. You need a lot less repeaters for fiber optic cable. Right, I'm still looking for disadvantages of fiber optic cables.
Not full duplex? It's not full duplex?
It's not full duplex, it's simplex. Yeah. What does simplex mean? Anybody here? Simplex communication, what does it mean? One-way communication only. Right, and what's the problem with satellites? Disadvantages of satellites compared to other devices.
Secure because they're being doing broadcast.
Okay, they're not secure because they're naturally broadcast, yeah?
And expensive initially.
Okay, leave the expense out of it because, well, unless you really verify, they can be cheaper. To start transmitting to everybody in Dublin, you're better off going for a satellite rather than a cable. If you are transmitting a distance of 200 meters within the college, maybe you're better off with a fiber optic cable instead of satellites. It'd be a lot cheaper. So unless you're really willing to explain, why is it cheaper or more expensive? Anything else? Same with fiber optic cables, by the way, yeah?
They can be affected with the weather condition.
They can be affected by the weather or by
The clouds.
electric storms overboard, coming across. Their signal is an electromagnetic signal. If it comes through an electric storm, it
I
can be a
think a
storm.
satellite can only last like 20 years, 35 years, while
Okay.
fiber optic cable lasts.
Yeah, they have a limited life, around 20 years. Oh, yeah.
There can be delays in satellites.
They have a delay. What's the delay in satellite? What's the delay? A quarter of a second delay. All satellites have a quarter of a second delay because the signal travels 36,000 kilometers up and 36,000 kilometers back, 72,000 kilometers, and speed of light is about 3,000 kilometers per second, so 330 actually, kilometers per second. So quarter of 72 is around quarter of a second, 0.24 of a second, exactly, yeah. So, okay, so that's media, we've covered media. Today I want to start another topic, and it's error detection. You probably have done part of it or some error detection. We'll look at error detection and error correction. Okay, so there are about 4 or 5 algorithms that we'll go through, we'll look through. Some are quite used a lot and some are less used. So the first one, well, I'll talk about, it's called the parity bit error detection system. You can't see what I'm writing, so is it? Right, so it's zoomed down a bit. Yeah. All right, parity bit. If you've heard of it, this is the system that's been around for the longest time, and it's the system that's probably still in use in systems more than any other. And not because it's a great system, it's just because it's been there for so long. And it's cheaper to leave it rather than to replace it or remove it from the system. So this is known as the parity bit error detection system. And the idea is simple. Every byte that's transmitted or stored, it's actually still used in every hard disk that you store. Every time you store a file, parity bit is included. And every time you want to read it, the operating system first goes and does a quick parity check on it, and it might tell you you have a parity problem in your error on the file. Every time you send a file, to be printed, it's checked. All this happens in the background. We are more interested in communication, so if you send a message from one place to another place, how is it checked for correctness, that this message has arrived as the sender has sent it, without any changes or modifications? Remember, every message you send is just a few bits of binary, a few hundreds or a few thousand or millions. The same as you store any information on any device, it is stored as binary. All pictures, videos, audios, everything stored in a hard disk or on any storage device, it's stored as ones and zeros. Everything transmitted, it's also transformed or transmitted as ones and zeros. So imagine if we have a number of bits, for example, being sent out. For argument's sake, let's say this example here where we have 3 and 7, 2, 4, 7, 1, 2, 3, 4, 5, 6. Imagine you're sending a string of bits and you're going to transfer it. The idea is simple. All you have to do is the sender, as they are sending the data, let's say data is being transferred this way, this one is sent first and keeps going. So as it's being transmitted, the sender will insert extra bits, and we call them the parity bits. And there are a number of, over the years, there have been like a few systems where they call it the 7-bit parity system, 8-bit parity system. They all operate on the same idea. So I'm just going to talk about one of them. And the other point is that the sender and the receiver also agree on something. They agree that are we going to use odd or even parity systems. The sender and the receiver must agree on this. So, okay, pick one, odd or even, and we're going to use it. Thank you for picking. Well, that's fine. Even. Did you pick even? Yeah, that's good. So we're going to use even parity system. Now the sender and the receiver must agree. So if I was the sender and I'm sending this data, the idea is, now we're going to be using even, for example. It doesn't matter whichever system we'll pick. Every byte I send must have an even number of bits that have the value 1. Must have an even number of ones. If we both agree the odd, then every byte I transfer or send or store will have an odd number of ones. But now we are picking up the even, so everything has to be even. So the sender inserts a bit at every byte. After 7 bits, we'll insert an extra bit. Some systems, they do it after 8 bits and they insert the 9th bit. Doesn't matter, we lose one of them. So now we're going to use every 7 bits, we'll insert an extra bit. So if we are going to maintain every byte, every 8 bits must have an even number. And that bit is the one that will make the difference that we insert, that will make sure then the number is even. So let's say, let's start sending this stream of bits. So the sender looks at the first 7 bits, 2, 4, 6, 7. Up to this point, there are 7 bits. I'm going to insert a bit here. I'm going to insert 1 or 0 in such a way that the 8 bits that the bit is going with, the parity is going with, will have an even number of bits. So it's like we count. How many bits are there? 1, 2, 3, 4, 5. That's odd. We must make it even. So we insert a 1. So we'll always either insert a 1 or a 0. So in this case, we insert a 1. So now the 8 bits will contain an even number, 2, 4, 6 bits that have the value 1. The next bit, the next byte, maybe let me change this. So, sorry. Okay, another one. 1, 2, 3. Oh, another 0. Right. So this one, the next 7 bits. That's 1, 2, 3, 4, 5, 6, 7. How many ones do they have? They already have 2 ones. That's already an even number. So shall we add a 1 or a 0? Add a 0 to maintain the number. So this byte has 2 bits that have the value 1. This byte here has 6. So every byte will have an even number of ones. That's the basic idea of parity error detection system. The last byte here, it has 3 bits that have the value 1. We'll make them 4. So the parity bit is going to have the value 1. And that's the way it goes. So it's very easy to do. And computers don't even have to count. What they do is a computer will take the first bit, and it with the next one, and the result with that, and leave the result there. And that will ensure that the number is an even number. So it doesn't even count. It performs either an AND or an OR operation, and that's extremely fast. So if you want to evaluate any program or algorithm, if it uses logical operations, that's AND, OR, NOR, exclusive OR, not, all these, that's what computers are good at and extremely fast at. Shift, left shift and right shift. Anything else, if a computer has to add numbers or multiply or divide, it's really slow. Fastest when computers do logical operations. So this system is extremely fast. It works really, really fast. Now, that's it. That's a simple system. Any issues anybody can spot in this system? Have you ever talked about this system or seen it or discussed it or done it in third year? Or?
We did it in second.
Good. So what's the problem with this system? It has 2 major problems. First, it's called redundant data. What's a redundant data? Redundant data is any extra data we send or we store that's not part of the user data. It costs. It's like if you operate a bus and the bus breaks down, so 2 of the seats you put 2 mechanics on that bus to travel with the bus. That's redundant weight, extra weight that makes you lose money, because instead of 2 passengers sitting on the seat, you have 2 mechanics. That's called redundant data. So redundant data is any extra data in communication systems and in transmission. Any data you transmit that's not part of the user data that you get paid for. You don't get paid for extra parity bits. They're handy for error detection, but not economically good thing to have. So this is one of the problems with this system. And you might say, it's not much. It's only a bit in every byte. But a bit in every byte, if you know that maybe we'll be transmitting millions of bytes every second, and a network may be billions of bytes every minute, and during a day, you can only imagine the amount of bytes. But if you transfer one file, if you make a transmission of 8 megabytes, 8 million bytes, 1 million of them is not data, it's redundant data. So the ratio is 1 in 8. So if these are 8 bits, one of them is a redundant data. They call that redundant data. The amount of redundant data is 1 in 8. If you're asked how much redundant data does parity system uses, or a ratio of 1 to 7. So it's either those 2 figures are correct representation of the amount of redundant data generated by parity systems. And that's one of its biggest problems. The amount of redundant data is huge. So when you compare another error detection system with this system, this will fail on this aspect. So that's one problem with this system. The other problem, anybody knows of another problem in this system? It cannot discover all errors. Does that ring a bell? What kind of errors it cannot discover? Any idea?
Is it something like if they put in whatever one it's searching, so it's other even, if they put in the wrong dish to make it other even, it wouldn't pick up what it's wrong?
Okay, maybe, I'm not sure if that's what, imagine if, for example, the idea in this is that if, for example, we are transferring this, and somewhere along the way, this bit, for example, flipped from 1 to 0, or 0 to 1, but this one changed from 1 to 0 during transmission. Now, when the receiver receives this and counts, how many ones are in the first byte? You count 1, 2, 3, 4, 5. Oh, 5 is an odd number. There's something wrong with this byte, and therefore the entire message is discarded. So that's how we discover normal errors as they occur, right? But imagine this. Imagine when we sent it, and originally there were 6 bits that had the value 1 sent by the sender, but in fact, these 2 bits flipped, that bit and this bit. So those 2 bits had an error. Now, when the receiver receives this and checks how many ones are there in this first byte and says 1, 2, 3, 4. He says 4, great, no errors, when in fact there were 2 errors in that byte. So this is the second problem, and it's a major problem again with this system. It cannot discover all errors. Well, there's no system that discovers all errors, but this one does not discover any time there are 2 bits in the same byte, or 4 bits, or 6 bits, or 8 bits. It can only discover if there is 1 bit flipped in a byte, or 3, or 5, or 7. So if there is an even number, so a better way to describe it, it does not discover even errors that involve even number of bits flipping in any 1 byte. So it doesn't discover 2 bits that flip in the same byte. Notice, if 1 bit flips in this byte, let's say this bit flips and that bit flips, there are 2 bits as well. Like if this bit flips to 0 and that bit flips to 0, will they be discovered? Yeah, the receiver will count how many bits are in this byte. 1, that's odd, that's an error. So if the 2 bits are in separate bytes, it will still work. If you are asked what errors, maybe you can phrase it nicely for us. What errors the parity system cannot discover?
When 2 bits flip in the same byte.
Exactly. But also when 4 or 6 or 8. So is there a better way of saying this? A more general way? What errors the parity system cannot discover? Yeah. When an even number of bits flip or change in the same byte, don't forget the same byte. You don't say the same byte, you don't get the mark for the answer. In the same byte, because if the 2 bits are in 2 separate bytes, then it will still work. So that's the end of the lecture. Okay, so that's the end of parity bit error detection system. What's the second system? The second system is known as the block parity system. And the block parity is based on this parity. It's just trying to solve this problem that if you have 2 bits or 4 bits on the same byte that cannot be discovered, it will actually discover them. So how does the block parity works? It works pretty much same as the normal parity system. So I'm going to use the same example, but I'm going to put the bytes one on top of the other, just to make them look like a matrix or a box. So it's the same bits here. I'm going to have 0, 1, 0, 1, 0, 0, 1, 1. And the next byte is 00. Oh, I'll put 11. Lots of zeros, 2, 3, 4, 5, and 1. And 2, 4, 5, 6. 2, 4, 5. Yeah, okay. Remember, parity bits are added by the sender, and so originally, that's the data. We have the data, 7 bits, and we insert an extra bit. The sender insert an 8th bit, and we call this, see all these here, the last. Okay, the magic touch, you know. Right, so the data, we just keep going through the data. Every 7 bits, we insert an extra bit called the parity bit. And that's the parity bit, inserted by the user, parity bits, and inserted by the sender. And when they are used by the receiver and we discover everything is good, they are removed. They're not part of the data. For example, you are downloading a file from somewhere, you know, a song or a video, every byte will contain an extra bit. Once your system checks it and finds it's good, throw away the bit, the parity bit, and just store on your hard disk the real file, the actual data. So this parity bit, these parity bits are inserted by the sender, they're removed by the receiver. And this is where, if, for example, those 2 bits here, like if we had 1 bit, if this bit goes into 0, then we should discover, hold on, are we working on even or odd? We said we're working on even. So this one here should have 4 bits that have the value 1. These ones here should have 2, that's great. And this one has 2. So every byte should have an even number of bits. That's how it is. Or if we agree on odd, then every byte must have an odd number of bits. That's done by the sender. And the receiver checks that. And when the receiver is happy, everything is good, we'll get rid of all these bits at the end. But of course, remember, if this bit flips, that's how it works. If this one goes into 0 and we count, we find only 1, that's how we know there's an error. But the problem is, for example, if these 2 bits, those 2 ones, or those 2 zeros, let's say those 2 zeros turn into 1s. So this is 1 and that's 1. So if we count 1, 2, 3, 4, 5, 6, we find that there are 6 bits. In fact, there are 2 errors, but the receiver does not recognize that. That's the problem with the with the parity error detection system. So let's do it. Let's make 2 bits flip. So it's easier to turn this into 0 and that's into a 0. I'll just underline them just for us to know these 2 bits were flipped. Now we do not discover them. So we go through 1, 2, 3, 1, 2, say, okay, there's an even number of 1s. That's good. Now, with the block, they said, as you do count horizontally, also count vertically and insert 1 bit at the very end of every column. That means at the end of all the bytes, you add 1 extra byte. Those bits that it contains are all parity bits. So, and you can have even parity horizontally and even vertically, or even an odd vertically. You can have either. Let's just keep things simple. We'll also have even vertically. So we have even check horizontally. There must be an even number, and also there must be even vertically. But remember, you can have, odd one way and even the other way. But we just keep it simple. So now, if you were the sender, if I was the sender, and I want to send this message, so I put the parity bits at the end of every byte, but also I put an extra parity byte at the end. So for this one, I'd count, that's 1. I'll add in another parity bit, 1, to make sure the total number is 2. These are 0, 0, 0. 0 is considered an even number, even though it's a 0. And similarly here, and there, and here as well. So because 1, 2, we already have 2, so we'll keep that. And here, 1, 2, 3, we don't need to worry too much about the parity bits, but we'll do it, and there it is 4. So now we have counted everything horizontally counts as even number, everything vertically counts as an even number. That's a 2 there this way. And so now we have our frame or packet that's transferred. It's counted byte cross, and at the very end, 1 byte. And if the receiver, when the receiver receives this frame and counts every byte horizontally, finds its even number, and counts every column vertically, finds an even number, it will remove the parity bits at the end of every byte, and it will remove the parity bits at the very end, the last byte. Now, is this good system? Let's test it out. Let's pick any 2 bytes or 2 bits, and flip them. So this bit, okay, let's flip the same bits. This goes into 1, and this goes into 1 as well. So this became 1 and that became 1. That's an error. So the receiver receives this frame now with 2 bits flipped in that byte. So the receiver counts horizontally, 1, 2, 3, 4. Says, oh, there are 4 bits. That's an even number, that's good, there's no error. And it keeps going, finishes counting this way. In the meantime, it's already counting vertical. So it counts the first column on the left, says 1, 2, that's 2, that's even. The second column, it has 1, that's an odd number, there's an error. And therefore, see the error that we missed this way, we can discover it vertically. And by a small bit, like that extra addition that we made, only 1 byte to the entire frame or packet, not a bit at every byte. So instead of, for example, if we had a frame or a packet of 4,000 bytes, which is, standard size, yeah, we'll have 4,000 bits added, but with this system, as well as those 4,000 bits, we add 8 more bits, which is 1 byte at the very end. So the extra cost is very little, but now it actually eliminates the problem of duplicate bits flipping, or 2 or 4 or 6 bits flipping in 1 byte. We would discover it. If we don't discover it horizontally, we'll discover it vertically. And that's called the block parity. So it's just an extension of the parity bit system. It's still expensive. It's as expensive as the normal parity system. It has every 7 bits you transfer, you'll require 1 bit. So it's still, the ratio is still 7 to 1 plus 1 byte at the end. It's insignificant, the extra byte at the end, because, for example, if you're sending 7 million bytes, 1 million of them is going to be, or you need to have an extra 1 million bytes of redundant data, plus an extra byte or 2 or 3. So, what's wrong with this system? This sounds like fantastic, very fast, because it doesn't count. It's a logical operation either way, easily done on the system. It's extremely fast, and now it discovers all errors vertical. It doesn't matter how many bits. Any issues with this system? Anybody remembers any problems with this system?
It might take longer to run this one because you have to be tracked horizontally.
Tiny bit longer. Remember, it's extremely fast. It's a logical, it doesn't actually count 1, 2, 3. It does ANDing. And the last bit leaves whatever result it has. Start the first bit, AND it with the next one. And the result, AND it with the next one. The result is AND it with the next one. So it's extremely fast still. What's wrong with it is that sometimes you get 2 bits, those 2 bits that flipped on that byte, there'll be 2 bits flipped on that column and 2 bits flipping on that column as well. Imagine if that bit flipped and also this bit flipped and also this bit flipped. Imagine this. Now we have 4 bits with errors. Okay. Just so you'd see them, they're in blue here. So that bit, those bits, and those bits, those 4 bits. And now we have 4 errors. And if you count them, if you count horizontally here, 1, 2, 3, 4, you say perfect. If you count this byte, you say 1, 2, 3, 4 as well. That's good. Let's count vertically. 1, 2. That's even number. That's great. And that's 2, also even number. So you'd miss all errors. Only in one case, if the 2 errors are on 2 bytes, and the 2 errors again are on two columns. This is the only error that cannot be discovered by this. It's unlikely to happen, but it's possible. Now, in general, if we can draw a box over this matrix, let's say any box, let's say a triangle, rectangle, if we draw any square or rectangle, see the 4 corners of this box. If that bit and that bit and this bit and this bit flip, they would not be discovered. Because you'd count with those here, they'll be on the same line, and those will be in the same line, on the same row, and these would be in the same column, and those 2 would be in the same column. That would not be discovered. This box as well, if I go this one, if you draw any rectangle, any box with 4 corners, and those 4 bits, one on each corner, flip at the same time, they cannot be discovered. So that's still the problem with this system, right? If that bit and this bit and this bit and that bit flip, they form the corners of another rectangle. So it's still a little bit weaker. It's unlikely only those 4 bits will flip. Normally, if you get an error, you get few beside one another, but it's a system, it's an improvement. It's not used a lot, but now you know about it. It's called the block parity bit error detection system. There's still, the parity is still in huge use, despite that it's not as good, and despite that it's expensive, as in redundant data, but still built into systems for so long that it's too expensive to remove it. The next system we look at is known as CRC, and that stands for Cyclic Redundancy Check. Cyclic Redundancy Check. That does check by cycling through the bits or bytes in a frame until it gets to the end. And it produces a redundancy, some redundancy, that we call that the CRC, that we send it at the end of the frame. How does that work? It works obviously in binary, but I'll just give you a quick example of how it would work on decimal systems. And then we'll switch to binary. But just to give you the idea is simple in CRC. Imagine if you have some numbers, for example, and you're sending the data. So this is the start of the frame, and this is the end of the frame. And we're sending, say, the number 13, 7, 6, what's that, 26, 4, and 3. Imagine, this is the data we're sending. It's just decimal data now. It makes a bit more sense to us. So what does the system basically do? It kind of adds them all up and divide them by an agreed key, a key that's agreed by sender and the receiver. We call it the generator. They call it the generator. That's the one that generates the error kind of code that we send at the end. So what's adding these numbers? Well, anybody has added them up? 33? I'll take your word for it, right. And let's say the agreed number is 5. This is the generator. Or 6, or any other number, but let's take 5. So what it does, it actually divides 33 divided by 5. And it has a decimal, it has a value. 33 divided by 5 is 6, and 3 is the remainder. The remainder is 3. It says, what is the complement? What would it take to add to this number to make it divide by 5 without any remainder, with remainder 0? What did he say? 2. Yeah, so now we know 3. The complement of 3 to 5 is 2. So if we put in a 2 here, what we will turn this frame into numbers. If they are divided by the agreed generator 5, they'll have a remainder of 0. So now, let's say the receiver received this frame. So this is now the extra redundant data that gets sent by CRC. Well, the receiver received this frame and includes all the numbers together and add them up. So 13 plus 7, 642, it's 35. Divided by this agreed number that both sides have, divided by 5 equals 7. We're not interested in the 7, we're interested in the remainder 0. It says then there's no error. If one of these numbers, let's say this 7 turned into 8. So the receiver, during transmission, turned into 8. So the receiver received these, adds them up, they're 36. Divide them by 5, it's 7, but the remainder is 4. It says, oh, once the remainder is not 0, that means there is an error. This is the basic idea. To do it in binary, it's a lot easier, a lot for the computer, a lot faster as well, and it works better. Because in binary, first, the operation, the division operation, which is a very slow operation for computers, we will not actually be dividing, we'll be doing a logical operation, and it's called XOR. So the XOR is like the long division operation that we always do. Now, the other good thing is that in binary, if you get a remainder, as the sender gets a remainder, that remainder is also a complement. You don't have to go and work out. Earlier on, we got remainder 3. What's the complement of 3? You work it, it's 2. No, in binary, 1 complements the 0, 0 complements the 1. So, in short, it works, and it works extremely well. And it discovers more errors than any other system known today, and it works faster or just as fast as that parity system, because it's a logical operation. And it's used on almost all error detection systems. And more than 98% of the networks use CRC. It's one of the best systems that's available today. It's still not 100% perfect, but hopefully maybe one of you will be able to come up with something, with some improvement and make it perfect. Let's see how it works. Now you need to know how it works. You need to be able to do the actual calculation as the computer does it. But let's do it. It's simple. It has 4 steps to do it. Let's first take an example. Here's an example. Let's say 110110001. For example, this can be a very long frame. This can be thousands of bits, or even probably millions of bits. No, thousands in a packet or a frame. And let's imagine the generator is a number that's 101, which is 5. Now, you shouldn't be doing this. If you get an exam, a question in the exam, you don't convert that to decimal, convert this to decimal, which is 5, divide that by that and get the remainder, put it there. That's not the way you should do it. We need it to be done as the computer actually does it, the algorithm that we have. Right. So first thing, step number 1, it has to be like the sender and the receiver. There's only one slight difference. One step is the difference between them. So I'm going to write the steps. if you are a sender and you're given this data, this frame or packet to transfer, and that's the generator, show us the data that you're going to send. The actual frame unchanged, but then at the end of it, you need to put in that extra, whatever redundant data. And as you can see here, immediately, you don't put a bit at every byte. You put maybe a byte at the end of a frame. So very little redundant data. The frame can be 3,000 bytes. You put 1 or 2 bytes at the end of that frame. So as long as the frame is, bigger than a few bytes, you're okay. You're saving already. So it has the least amount of extra data that's sent. So that's one advantage of CRC over the parity. This is the first advantage. Now, step number 1 in this is first just make sure you know where's the data. Identify your data that you need to transfer. That's the frame. You're given some information, say send this. And in this case, the generator, that's the number. So the generator is a number agreed between 2 sides. And it's not a secretive number. And some numbers, some generators work better at detecting errors than others. So back in the 70s or 80s, scientists and mathematicians sat down and they found the best numbers that can actually produce the best results. And when they issued the standard for CRC, CRC is a standard, an error detection standard, international standard. They actually also produced, they said, these are the best numbers you should use if you want to use, a generator in your network. And it's one generator for a network everybody uses, so it's not a secretive number. But it's already recommended by the standards organization. They have maybe 4 or maybe 6 numbers. So your network will pick one of them and say, okay, you join the network, they tell you, here's our generator. You need to use the same generator for your error detection. But anyway, for now, that's our generator. It's a very simple one. And that's our data. This data can be thousands of bits. So we know them. Now, second item is insert zeros. Not insert, its better word is append zeros to the data. That means you put it at the end of the frame. You put data at the trailing edge of the frame, not the part that's being transferred, the tail part of it. How many zeros? 1 0 less than the length of the generator measured in bits. So our generator, there it is, 3 bits. If our generator was 13 bits, then you insert or append 12 zeros. This is 3, you append 2. So always 1 0 less than the number of the length of the generator in bits. So whatever length of the generator in bits that you are presented with, if it's 10, that means you're going to insert or append 9 zeros. Always 1 0 less than the length number of bits in the generator. And this step is only done by the sender. Sometimes you are presented with a problem and you're told you're the receiver. Can you check if there is an error? And at least in every 10 students in every exam, they always end up inserting zeros when they're doing the receiver's job. This step is only done at the sender part, inserting those zeros. Right, so basically I'm just gonna insert 2 zeros at the end of this. Step number 3, start the division. Divide. And remember, it's not a real division. It looks like division. It's in fact, it's XORing. Does everybody know what an XOR is? Yeah, even if you did, I'm gonna tell you anyway. So XORing. So OR, do you remember the AND and the OR? The OR is simple. The circuit for OR is like if you have a battery and there are 2 switches, switch A and switch B. And they both meet again, and they switch a light on or off, and there it is. This is the OR diagram. You probably done it in first year. What does OR mean? It means if this switch A is closed, it's 1, the light will come on. Open it, the light off. If you close B, the light will come on. So it's either A or B, or both. The light will come on. Exclusive OR is the same as OR, except not the two of them. Never switch the two switches. Don't close the two switches on. If you close them, the light will not come on. It's exclusive. Only one of them will work. So I'm going to do the table for exclusive OR. If you have the two switches A and B, what's the result? Will the light come on or not? If both switches are off, can you help me? No light. If first switch is off, the second one is on, there is light, yeah. You need to follow me up just to make sure I don't do it wrong. If this is XOR, that means if the two switches are on, there'll be no light. That's the difference between OR and exclusive OR, the last line. All right? Now, that's like a division operation. We'll see how actually a division operation works. But the point here, just for me to remember, you probably have no problem remembering this, but an easy way I find to remember, if the two switches are zeros or the two switches are ones, the result is 0. If the two switches are off or on, the light will not work. If only one of the switches is on, then the light is on. So that's how I remember. If the two of them are similar, the result is 0. If they're different, the result is 1. That's the way I remember it. You think of any way, as long as you remember it and it works well for you. Let's see how this works. Now, so we've done 2 steps. We identified, we know that's our data, that's the generator. We inserted zeros at the right-hand side, or appended zeros. I keep saying insert 0. We appended zeros at the end of the frame or the data. And let's start the division operation. In fact, it's XOR. It's a long division. I don't know if you ever done long division, but that's the way they used to teach us how to divide in school. So you take the big number, and that's the divisor. You want to divide it. Now, you always need as many bits. You start with as many bits as your generator. Like you can't divide, say, 5 divided by 78. If they have to be, they have to have the same digits. So if this one is 3, you must start with 3. If this one is 5, you must start with 5 bits. If you have less than 5, if what you have left is less than that, then you're finished. You cannot continue the division. Right, so let's do it. So usually we divide this divided by this. This is like even in decimal, 110 divided by 101, but we are looking at binary. So in binary, the result is 1 or 0. If that's, the same number of bits, then the result is 1. And then you multiply that into that, and you put the 101 here. And in long division, we subtract to get the remainder. But here's where the slight difference, we XOR. So 1 XORed with 1. See, the two numbers, the two digits or bits, the one on top of the other. So 1 XORed with 1, there it is. The result is 0. That's where it comes in handy. If they're different, that's 1 and that's a 0, the result is 1. I don't even have to think about it anymore. And that's 0 and 1, they're different, that's the 1. So we're finished with the first step. Now we do it. Any 0 on the left, ignore it. But sometimes we don't ignore it and we start using it. So I recommend that you mark it off, it's gone. So you will not be using it again. And now we have to bring in 1 or 2 or 3 bits from the ones that we have from the rest of the frame. That's how, in reality, the algorithm will be going through the data. But now, in division, we bring this bit down. We always bring as many bits as you need. This one, you need 3 bits. If we only had 1 here, then you need to bring down 2 bits. But now there it is. We have 3 bits available. And also mark the one you bring down, just in case you start bringing them twice down and you get the wrong result. Now, divide this by that, you don't need to put any information there. We don't need it. All you have to do is write the 101. So you just keep writing 101 underneath and perform the XOR. Right, okay. Loud enough, give me the numbers. 0.
0, 1, 0.
Thank you. And let me cross out the 0 on the left. 0 on the right has value, but the one on the left is no good. Now, we bring down the next number. How many bits do I need to bring down? Only one. That'll give us 3 bits. That's 3 bits. That's enough. And we also divide and just insert the 101 here. What's next? XORing them. 0, 0, 0. Whoa. And they're all zeros, and get rid of them. Now, how many bits do we need to bring down? At least 3. So we bring this 0. The 0 is no good on the left. Bring the next one. 0. That's no good. Okay, so sometimes it happens. Now we bring the next bit. It's 1. The next bit is 0. And the next bit is 0. Whew. Now we bring down this again, 101. Once we have 3 bits. Yeah, what's the result here? 0, 0, 1. And that's it. No more bits to bring down. We don't have 3 bits, or as many bits to continue. The operation is finished. So dividing that number by that generator gave us a remainder of 0, 0, 1. Of course, zeros on the left are no good. So it actually gave us possibly, if this was, 31 divided by 5, it would be 6 and you have remainder 1. If it was decimal, but it's not decimal, it's binary. But that's how it works. Now, we finished the operation. Normally, this algorithm will be going ANDing, or XORing, and whatever is left, it leaves it at the end instead of those zeros at the end of the frame. And that's our redundant data. So now, what do we send? The original data, don't forget, that's our data. That's 1, 1, 0, 1, 1, 0, 0, 1. Those 2 zeros are not part of it. Now, that's the remainder we'll have to add in. How many bits we must write here? 2 bits, the same as 1 less than the length of the generator. Like we put 2 zeros here, we must put 2 bits here. So if it's a 1, that's only 1 bit. You can pad it with zeros on the left. Sometimes you get 1, 1, okay, then you put the 2 of them there. But in this particular case, there's only 1 value, 1, but we need to pad it to make sure that we put 2 bits. And that's actually now what gets to be transmitted. This is our frame with the CRC at the end of it. That's the redundant data. This operation is so fast because it's an XOR operation. In fact, it's so faster than even XOR operation because in this algorithm, it's the only algorithm that you don't have to wait. The sender does not have to wait until the operation is all calculated and the number is, generated at the end. The moment, for example, this is a very long frame or packet. The moment the algorithm starts calculating and goes past a byte or 2, the transmitter, the physical transmitter, starts transmitting data. And this guy is ahead of it, calculating while this one is transmitting. When this one is finished, it will leave those remainder, they'll be left there at the end, it gets out of the way and the transmitter sends it. So it's fast, but second, you don't have to wait until it does the job. The moment it starts, the transmitter can start immediately after. Therefore, you're not wasting much time. The transmitter is sending data and is probably going ahead of the actual transmitter. So it's probably faster than the transmitter as well. So it's an extremely fast algorithm. Now, so this is as a sender. Let's see if once you receive this information, this frame with this end of it that has a CRC, how does the receiver check out whether there is an error or not? You need to be able to do this. We'll do it now in a few minutes. But let's do the operation that's performed by the receiver. First, let me get the information. Please check that I'm getting the correct information here. So we receive this frame 1101100101. That's the correct frame. Now, and we used, the receiver should already know that the generator, the agreed generator is 101. Now, and now we are at a receiver end. Now the sender, sorry, just the last step here of the sender, I did it, but I didn't write it, just so you'd know. After you finish the ANDing or the division, and you're left with the remainder, you just append the remainder to data, to original data. Remember, you need to get rid of those 2 zeros and replace them with the remainder. So these are the 4 steps that are done by the sender. Now let's see the receiver. Receiver now receives this frame or packet. First step, receiver needs to identify data, generator, and CRC. CRC meaning the addition that was added by the CRC. They call it CRC. And the field, in some networks, they call it the frame check sequence. FCS frame, the little frame where they actually put that CRC, the extra, the redundant piece of information that will. So anyway, so how does a receiver know which part of this information is the actual user data and which part of it is the additional kind of calculations? Any idea? You get a frame, pardon?
3 bits because the generator has 3 bits.
Yeah, because the receiver knows the generator. If the generator had 10 bits, that means the last 9 bits here are not really part of the data. So if after performing a check and you've realized, okay, there's no error on this information, you have to get rid of the redundant data, the extra CRC. So how does the receiver know? It knows from the size of the generator, it knows where at the end of the data, how many bits will I get rid of. And that's based on the length of the generator, because it knows how long the generator is. All right, let's start the operation. So first you identify. Number 2, you should start dividing, but I'm going to write another step. Do not what? Append zeros. Like normally you don't write a step, of instructions telling somebody how to make a cake and you say break the eggs and all that. And listen, do not put salt. But you don't normally write that. But here I'm writing it because there's always 1 or 2 students who will actually append zeros and they get completely wrong results. Please do not append zeros. I'm writing it down. Number 3, then just start the division. Start to divide. But remember, at this stage, it's not really division. It's XORing. I hope you know it. So, okay, who's going to help me here? You look like the least interested party here. You're almost fallen asleep. So, you're going to go through this, right? Now, the division operation, the XOR. You lead, you tell me what to do. Right, I'll just put the 101 here. You must start with 3 bits and tell me the values.
0, 1.
You get rid of this. Right, how many bits will I bring down?
1.
Oh, that's not 101.
0, 1, 0. And then 1. Now we have to break, yeah. 1, 1. 0, 0, 0.
So now, and that's the end of the division operation. After sending that, see those 2 numbers here, those 2 bits that were inserted, they were actually the complement that made that number divide over that number without any remainder. That's the complement that when we were doing the decimal. Now, that's the last and final step. Now, if this number was not zeros, if the remainder does not equal 0, then it's definite error. We have an error somewhere. Let's try that. Let me take the same data, 110, 1100101. That's the same data as we started with, and we're going to divide it by 101. But now I'm going, can you look away for just 2 seconds? There it is. I'm after flipping one of the bits. You don't know where it is or which one it is. Right. Who's one of you guys? Please help me here. Let's finish this. This is the data we received. We've done the same thing. We have, so we know at the end there's CRC, and that's the generator. Now, let's divide 101. I'll tell you which bit later on, but for now we don't need to know. Right. You're going to help me.
011.
Right, bring down the next one. It's 101. Yeah?
011.
Oh, all right. Next one is 1. So it's 101.
010.
All right. I'm going to extend it, I guess. Yeah. Right. Bring down 2 zeros. How many bits will I bring down? Another 0? No, we have 3 bits. We have as many bits as we need. You always need as many as the generator length. So 101.
001.
Well, how many bits will I bring? 2. That's right, yeah. So it's 101. No. Right, how many bits will I bring?
2.
Okay, zeros on the left are no good. So now we don't have enough to continue. We're finished. And the remainder is not 0. Whatever the remainder is. If it's not 0, it's definite error. Right? So that's the note I wrote there. If the remainder does not equal 0, it means definite error, 100% error. But if the remainder equals 0, then what does that mean? There might be an error, yeah. It's most likely, you can't say it's 100% correct, even though it's very close to 100%. We'll see later on how close it is. Very, very close. But you can't just say it's error-free or 100% error-free. You must say most likely no error. And this is the last mark in your question exam. If you write, the remainder is 0, that means no error. You don't get that 10 out of 10, you get 9 out of 10. You got that far. But it's for not being very accurate. There could still be an error and cannot be discovered. Right, so this is the CRC done by both the sender and the receiver. I don't know where the sender is, there it is. Right, simple enough, guys. Right. This is the data, and that's your generator. And you are a sender. Please send this, generate whatever it takes. You need to generate the CRC for this frame. And show me the frame, the entire frame that gets transferred or transmitted. That's this original data with the extra CRC that you will produce, the number of bits. So now please do this. You have 4 minutes or 5 minutes. If you don't know how to start, put your hand up. And if you don't, unless if you don't have a paper with you or a notebook. Who doesn't have a piece of paper or some means of writing? You don't? Guess what? I happen to have one for you. You want one? You can work it on your laptop as well, but yeah, okay, fine. No, there you are. You know, do you want a pen?
Yeah.
Remind me, guys, next class for the part-time group, I'm gonna bring a new box of papers and box of pens. Anybody else for a pen or a paper? Come on, I have plenty. Yeah. Pen. Oh, then I have to dig deep in my pockets. Oh, there. Oh, guys. Okay, that's welcome. And well, I was gonna say. Let me check first. Do you want one? Let me check this first. What's the date? And also a piece of chocolate for the first to finish this. You are at a clear disadvantage now, this guy who's still waiting on paper. I don't have a pen. I'll give you one of my markers, right? It's purple, right? With pink. I'll see if you want it. What do you want to say? Right, you got chocolate here for the first correct solution. Anybody has a problem, let me know. You finished? Now, who finished first? Who of you guys finished first? Okay, so you append, these are the instructions, right? I got 5 and 2 zeros. Oh, yeah. Okay, there's an error in my data. Hey, so that's good. Sorry, guys. This one is a 0. This one is a 0. Sorry for those who started. My apologies. Those three, they thought they were winning. You're almost there?
No, at the first time around.
Okay, so then I get into chocolate then. Anybody doesn't know how to start or how to go about it? Well, then before I forget, I need a student, class rep. Are you finished? Who's finished? You finished? Yeah. No? Oh. Just being, you're showing off, right? But you're losing the chocolate now. Okay. Come on, guys, I've just finished. What's your remainder? Huh? What's your remainder? Congratulations. Was it you? 101, right? Yeah. Oh, you also? Okay. Are you finished? Yes? All right, let me go through. That's not the remainder, that's not the final result, but still. The final result says, what frame will you send? You'll send that frame, appended to it, that CRC value that you got behind it, appended to it. That will be the final result. All right, this is the way to do it. I'll give you another example after this, but then we'll take a break. Right, let's follow the steps. As a sender, don't forget you're a sender now. You're going to send this user data. First thing, you identify your data in the generator. That's simple. That's the data, that's the generator. Generator is 4 bits long. Right, the next step is append zeros to the data. How many zeros do we append? 3. Why? Because the generator has length of 4. Right, now start the division or XORing. Right, so you just place 1, 0, 1, 1 here, and you end up getting 0, 1, 0, 1. Eliminate the 0 on the left, bring down the next one, and that's 1, 0, 1, 1. And that brings 0, 0, 0, 0. 4 zeros, they're all gone. Bring down the next 0, it's useless, no good. 0 is no good. So bring down the 1 and 1 and 2 zeros. 2 of those 2 zeros. 2 of those 3 zeros. So now all zeros on the left are no good, so that's 1, 0, 1, 1, and that gives us 0, 1, 1, 1. Bring down the next 0, and that's 1, 0, 1, 1, and that gives us a 0, 1, 0, 1. Now we have to, these are 4, that means we take those 3. Get rid of this 0. So we always take 1 less. So we take the original data, which is 1, 1, that's the original data, 1, 0, 1, 0, 0, 1, 1, and append to it 1, 0, 1. And that's the frame that leaves.
I asked before when it resulted in all zeros. If that was to happen, would you just put 3 zeros on the end and send that?
If this was the end of the operation, yeah, that means that number actually divides without a remainder. If that was the end of the data.
Yeah.
But, yeah. And originally that's what we had. That's why I changed the bits just to make sure, you know, the number I picked by randomly, it just happened to divide without remainder. Right, now, this is the data we got. And this is the final example now you'll do on CRC. Well, if you do this, then you're all right. Now I'm gonna put some data. Maybe it's the same, maybe it's slightly different. You are a receiver, and I want you to find out whether there is an error in this data. And the generator is 1011. So this is a received frame. This is a received frame, and that's the generator that the sender used. You are a receiver. Does this frame contain any errors? That's the question you get in an exam. Does this frame contain, this is a received frame. Does it contain any errors? So you need to do the CRC check by the receiver and see what the remainder is. If the remainder is not 0, that means yes, it contains an error, discard it. If it's free of errors, if the remainder is 0, then most likely it's free of errors, and just extract the data. Get rid of the CRC. Go on. 4 minutes to do it. Okay, you can do it on the other side of the paper, please. You want the viral again?
Yeah.
No, not about chocolate, that's why. If you have an issue, let me know. That's why I have started. This is the most used algorithm in computer networks and communication. We've done this before. So not repeating the course, right? I used to teach first and second years, or no, third years.
It used to be second year, we were the first one, we had first year class
All right,
for operating systems.
yeah. And then I used to teach the NDC, the third year network. I don't know who taught you that, maybe Tomas or.
Yeah.
Okay, are we nearly there? Right, I'm gonna go through it. Has anybody got any results? What's the remainder? Yeah, what's the remainder? 111. Okay, somebody is gone. All right, let's see. Maybe we'll take back that bar of chocolate now. Right, okay. Who's got? All right, you're gonna help me, right, for a change. All right, I'm gonna start dividing. What are the steps? Shall we add few zeros here? No zeros are appended by the receiver. Right, we start the division almost immediately. So 1, 0, 1, 1, and the result is?
1, 0, 1.
How many bits will I bring down?
1,
Yeah?
0, 0, 0, 1.
How many bits will I bring down?
3.
Yeah?
0, 0, 1, 0.
Right, how many bits will I bring?
2. 0, 0, 0, 0.
That's the end of the operation. We have a remainder. Yeah. Okay, maybe it's time for a break before we go into Hamming code. Hamming code is the error detection correction algorithm. Any questions? Actually, what time is it now? Yeah, no, break time. Couple of points I want to mention on CRC. Okay. So now we've done parity detection systems and block parity and CRC. The CRC is just a couple of notes that we need to know about it. That when CRC started back in the 70s and 80s, international standards came out to just define it. And a lot of research was done by mathematicians to find out the best generator, the number that will generate or discover more errors. And they came up with a list of maybe about 4 or 6 of them, numbers. And they are the ones that are used. They are published with the standard, so every network will use one of those numbers. And everybody has to use the number. But when they give you the number, whether you're a programmer, for example, you want to insert that number into your code or somewhere in the system, they don't give it in binary. Of course, that would be too simple, right? So they give it in a different format, and that format is known as what is it known as? Polynomial format. So the polynomial format for a number, they said if we give it in binary number and you get a string of ones or zeros, that it's very easy to make a mistake by the person who is reading that and have an extra one or an extra zero or one less one or less a zero. So they don't actually give you the polynomial in binary. And consequently, everybody follows the rule. And when you get an exam question and we give you the data and we give you the generator, we don't give you generator in binary. We give it to you in polynomial. So what does a polynomial format look like? It looks like this. They only give you representation of the ones. They ignore the zeros. You have to fill in the zeros yourself in the generator. And they give you the representation of one. The one is represented by x to the power of some number. For example, x to the power of 6 plus x to the power of 3 plus x squared plus 1. This is a key, written in polynomial format. Each x here represents 1. If the x is missing, that means it's a 0. And just one other point to note about the generator, it must start with 1 and it must end with a 1. You can't have a 0 on either side of the generator. It always ends with 1. And 1 is this one here is the x to the power of 0, but instead of writing x to the power of 0, they write 1. So how do you convert this number? It's simple. You start with the x with the largest one that you have, and that's replaced by 1. You go to the one before it. This is x to the power of 6. Is there an x to the power of 5? There isn't, so it's replaced with a 0. Is there an x to the power of 4? No, there isn't, then that's a 0. X to the power of 3 is there, that's a 1. The one next to it, x to the power of 2 is there, it's 1. And then x to the power of 1 is missing. Remember, that one represents any number, anything to the power of 0, the result is 1. So that's x to the power of 0. So what we're missing is the x to the power of 1, which is 0, and then finally that 1. And this is now the equivalent of that in binary. And you have to do that in an exam. You're given a generator in polynomial, so first you convert it into binary, and then do the either as a sender or receiver algorithm. So if you get this wrong, then the rest of your work is probably wrong as well. So make sure you know how to get this right. I'll give you one more example. Let's say x to the power of 4 plus 1. This will be x to the power of 4 is 1. X to the power of 3 is not there. X to the power of 2 to the power of 1 and 1. So x to the power of 4 is the representation of 1, 0, 0, 0, 1. Is that clear? Good. Like the way you nod your head, so maybe you can help me with this plus x plus 1. What's this number, please, in binary?
1, 1, 0, 0, 1, 1.
Okay. Cup of tea, right? So no problem. Good. What about this? X to the power of 4 plus x plus 1. Oh, no. That's so simple, isn't it? X to the power of 6 plus x to the power of 3 plus x plus 1. One of you, gentlemen?
1, 0, 0, 1, 0, 1.
That's it.
1, 0, 0. Is that right? 1, 0, 0, 1.
It looks right to me. No, it's wrong. I think it's probably another one. Okay, so this is it. Okay, so everybody is okay with this? Right. I knew it wouldn't be a problem. Yeah, but I had to lead you to their own conclusion. Right, so that's one thing. The other thing I want to tell you is how many errors, what errors this CRC can discover or cannot discover. Right, I'll tell you what it can discover. So in an exam question, it could be asked what errors it can or cannot discover. So probably you say it can discover the following, it cannot discover anything else. CRC can discover the following errors. First, if the error involves bits, that means the bits that flip less than the or equal to the length of the generator. So if the generator is 10 bits, then you get 5 bits of error, or 7, or 9, or 3, or 1. They'll be discovered at 100% will be discovered. They'll all be discovered. So provided the number of bits that are in the frame, not in a byte now, we're talking about the entire message, the frame or the packet. As long as the number of bits are less than the generator, they'll be 100% discovered. Now, we only have to worry about anything longer than the generator. If they're longer than the generator and odd number of bits. If they're odd, that's the important keyword, it's 100%. So to discover any errors of 33 bits or 27 or 19 or any number like that, but not 42 or maybe 18 bits, may not discover them, may or may not discover them. So now what are we stuck with? Longer than the generator and even. So if the number of bits that have flipped, that gone into error, are bits that are in error, are longer than the length of the generator, and if they are odd, would they be discovered? Yes, because the second rule will apply to them. And, this is a logical and, even number. Like, the generator is 15, but we got 22 bits with errors. That's longer than the generator, and they're even number. It will discover them by 99.9%, the discovery rate. So as you can see, it will discover a huge amount of errors, the very, very few that it may or may not discover. Okay, that kind of ends our talk about CRC and what's the other one? Parity bit error detection systems. Now let's talk about Hamming code. I don't know, number 4 at this stage, Hamming code. And the advantage of having Hamming code is that this technique doesn't just detect errors. Remember, CRC detects an error, but it doesn't tell you which bit. And I have a question. If somebody sends you a frame or a packet and it has an error, how is that error corrected? How do we correct errors on networks? It has to be retransmitted. So that's the only way to correct errors. So far, on all networks today, that's the only way to fix errors on frames is by retransmitting those errors. Now, Hamming says, no, there's no need to retransmit. If we can define which bit or bits that flipped, and we can switch them. If it's 0, turn it to 1. If we knew this bit is the one with error. If it's 1, turn it to 0. If it's 0, flip it back to 1. And there it is. You don't have to retransmit the packet. That would be great if it works. So let's see if it works. So Hamming code is based on parity system. Same idea as parity, right? But what it does, instead of one parity, it makes parity intersects, depends on one another. I'll give you, again, a simple example that describes the idea, and then we implement it onto data communication or networks or frames and packets. Imagine if we had 3 areas of data, and let's say this is our string of data. Very simple, few bits. And if we can make those bits, split them into groups, and in this way, so it's easier to do it than actually to talk about it. Imagine if we have 3 areas, area A, area B, and area C. Right, and we're gonna have, this is data, the first bit, bit 2, bit 3, bit 4. If we put bit 1 here, bit 2 here, there, bit 3 there, and bit 4 there. Right, so a few bits landed into different areas or groups. Like we just split the data into few groups, but these groups intersect with each other. Now, looking at that, let's look at each group independently and do a parity check. I asked somebody earlier on, are we gonna select even or odd? Was it you? And what did you select earlier on? Or do you want to select now something? Shall we use odd or even? I think last time we used even as well, but we'll use it.
No, odd. Yeah.
We use odd. Do you want us to use odd now? Yeah. So, right. What do we mean by odd? Every group must have an odd number of bits that have the value 1. So we need to add to each group, add to it a parity bit. So let's start with group A. We want this group to remain odd. We're going to add another bit here, a 1 or a 0. In order to leave everything odd, what shall we add? A 1 or a 0? A 0, because we already have 3 ones. Right, let's look at group B. Anybody here on this side want to take it? Yeah? We add a 1. So now we have 3 ones and a 0, and that's odd. Now, the group C. What shall I add? A 0 or a 1? A 1, yeah. I'm going to make this back into this. So now we have a collection of data and parity bits. Now, I want you to look away for a second, and I'm going to flip one of those bits, and let's see if we can find out which one it is. Right? Nobody knows which one it is. Now, let's start. Now we want to find out where the bit is. Let's go through the groups again and check every group individually and find out, is that group okay or it has a problem? Group A. Is group A okay or has a problem? Does it have an odd number of ones? Just the circle A. How many ones does it have? It has 2. They should have been odd, but they're not. That means there's a problem in A. So we have a problem with A. What about B? Yeah? B has 3 ones. So it has no problem. It's good. What about C? It has a problem. So now we have a problem in A and C, but we have no problem in B. Right? What is common between A and C that's not really common with B? So A and C, they intersect in those 2 bits, the 0 and the 1. So it could be one of those. Now we want the one that's not, has no problem. The one that intersects with B is not in the equation. So that one is out because B has no problem. Then that leaves us with this 0. You see how they pinpoint the bit. So all we have to do, we have the data, and we have those 3 bits that we're going to insert 3 bits somewhere. They're called parity bits in this data. And we can tell if any bit flips, we can figure it out. Well, that's the basic idea. So let's see how it's actually, we can do it on a frame, on a kind of flat side, which bits are grouped together. So we're going to have 3 or 4 groups or whatever number of groups we need in such a way that can be easily detected. So, but you can see the idea. Right, let me have another example. Right, again, look away, guys. Right. Go through the sequence. Find out which bit has a problem. Tell us, talk to us while you're doing it.
So firstly check.
Group A.
Yeah, I see there are 2 ones, so.
So it has a problem. So A has a problem. What about B?
B2, so.
It also has a problem. It should be odd, but it's not. What about group C?
Also see as
Oh. So now, which bit actually intersects with the 3 groups? Like, that's the only one there that's part of A, also part of B, and also part of C, and that's really the one I actually, flipped without you noticing. So we'll fix it, and now everything goes back to perfect harmony again. So it's a wonderful, simple system to implement. Right, let's see how, and you need to know how it's done on a frame by the algorithm. Any questions so far? No? Good, that's what I like. Right, let's take some data and let's put it into a frame and put the parity bits as well. So let's say 1, 2, 3, 4, 5, 6, 7. This is the data we want to send. Now we're going to put it into a frame. Now, the frame must have 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever number, we'll fill it up if we need. So this is it's good to have the positions numbered. So this is position 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So it goes for as long as your data is. Now, where do we place the parity bits and how many parity bits we need? It's simple. Every power of 2, that's a parity bit location. Power of 2, that means 2 to the power of 0, which is 1. That's location 1. And just double that. Location 2, location 4, location 8, location 16. These are reserved for parity bits. Don't put data in them, right? So this place here, that's parity. I'll mark it, I'll write underneath it. This is parity location 1. They call this parity 2, parity for location 2, not the second parity bit, it's parity location 2. And this one, this is the 3rd bit parity, but we write on it parity 4. That means it's parity bit, that's called location 4. And this would be parity 8, and so on. And if there's more data, then we go to 16, 32, 64, and so on. So that's simple. So it's very clear, we know where to place our parities. Now, put in your data into the frame, but don't touch, just avoid the parity places. So start filling the data. The first bit goes in there, first available bit is the 3rd location, and that one goes there. And follow me, I make a lot of mistakes here, so please, right. And that's another 0, 0. Okay, that one doesn't go there, that's a parity 8, so it goes in the next location, 1, 0. Okay. I got the number right, Ali. So that's our data, we put it into a frame, and we have the parities. Now, which bits go with which parity? The way to go about it, for each parity, use the parity number. It has P1, P2, 4, 8. Start always, let's say parity N. Go to start position N. Take N, take bits number, N number of bits. That's 1. If it's 1, just take 1 bit. And then skip 1. Skip in, skip N. Right? It doesn't sound, but this is the way I remember it, it's easy. So if we are talking about parity 2, you go to start at number 2, you go to this location, take 2 bits, this one and that one, and skip 2, skip 4 and 5. And take 6 and 7, skip 8 and 9, take 10 and 11. If, for example, parity 4 we're talking about, you start at number 4, you go there, you take 4, take 1, 2, 3, 4, that's position 4, 5, 6, and 7, and skip the next 4, 8, 9, 10, 11, and keep doing until you reach the end of the frame. Okay, that's the general idea. Let's start. I'm gonna write here parity 1. What bits? Like it'd be nice on a table. So we're gonna take this parity 1, which we don't know what value it is. Now we're as senders, you're gonna put a 1 or a 0 here. We don't know what it is. Neither is this one 4 or 8. We don't know those values yet. We're gonna fill them in. Remember, we are working on, did we decide? Are we working on odd or even? Choice is yours now. Even is even, right? No, okay, now we go for it, go on. Right. Let's start with 1. We go to 1, we take it, we don't know what value it is yet. We skip 1, we skip number to position 2, and we go to number 3. Number 3 is 1. Right, so we skip 4, and we take the value for 5. We skip 6, and we write 0, which is location 7. And then we skip 8, and we take 9, and we skip 10, and we take 11. Okay, so we take every second bit, basically. They make the group, like group A we had. These are the group A, the first group. Now, we are gonna be using odd. Let's see what value do we have. Remember, the parity, we have not inserted the parity yet. We have to put 1 or 0 in this place. In order to make these odd, let's find out, are they odd or even already? 1, 2, 3. But they're already odd. That means this P1 has to be a 0. And that's what we end up writing here, 0. Right? Let's now go for number 2. Okay, anybody would like to help me based on this? Take 2, go start at 2, take 2 and skip 2. Okay, you look like somebody who wants to help me. Right? Yeah, I just see that you want to help me there. So where do I go? We're gonna be working on parity 2. Where do we start? Which column here? We start at number 2. If we are working on parity 2, we have to start at number 2. Right, so we're gonna start at this location. How many do we take? We take 2. We take this bit and that bit. This bit, we don't know what it is, and that bit is 1. And then we skip 2. We skip 4 and 5. Okay, are you with me? Yeah. Right, and now we take 6 and 7, which is 0 and a 0. This is the group that mixes up with, that makes up the parity 2 group. Then what happens? We got those 2, 6 and 7. We skip 8 and 9, and we take 10 and 11, which is a 1 and a 0. Right, do you understand that? This is the parity 2 group. We start at position 2, we take 2 bits, and we skip 2 bits. We take 2 bits, we skip 2. The 2 bits are at the top there, the original bits. I'm doing it now in tables. You can actually, later on, you'll be kind of doing it right on the data, but to make it easier now and clearer, and maybe in the exam, I want to see your work rather than come up with the final result. So, what do you think? You're still helping me. Am I going to put a 0 or a 1 for this parity bit 2? We're working on odd parity. You count how many 1s do we have? 1, 2. So what does the parity, should the parity have a 1 or a 0 in order to turn this group into an odd parity? Yeah, we put a 1, so now we have 3. Now we're happy. Okay, do you understand that? Who's going to help me with parity 4? Anybody there in the back there want to help me with parity 4? Yeah, go on. Here's parity 4. Remember, we have parity 4 and parity 8 so far. Yeah. Where do we start? We start at column 4. There it is. That's the column 4 we're going to start. We don't know what value that is. How many bits will we take? 4. So I take the 1 and the 0 and the 0. And then we're going to skip 4, 8, 9, 10, 11. Skip, and that's it. We got to the end of the packet. If there was more data, then we start the next 4. We take the next 4 after that. Now, are they already odd or even? And what value should I put in this bit? 0. We put a 0. So to maintain an odd number, there's only 1 here. 1 is odd, so that's perfect. Then this one had a 2 even, and therefore we insert plus, we put a 1. Right, the last one. This is a special one for P8. This is for you.
So go to column 8.
We go to column 8 and we take 8 bits. We go to start at 8, take 8 and skip 8, take 8, skip 8. So we go to 8, we take 8, 9, 10 and 11, and that's it. We don't have any more. Now, there are two which is even, and therefore the parity bit, will it have, what value will we put on it? Sorry. 1. That's it. So this one has a 1, this one has a 0, number 2 has a 1, and number 4 has a 0. And there it is. This is the data that we'll end up sending. So if you're asked what's the frame that will be sent, there it is. 0, 1, 1, 0, 1, 00, 111, and a 0. This is the frame, including the data and the parity bits, using Hamming code. This is coded with Hamming code. Now, let's see now how the receiver will react. And later on, we'll flip one of these bits and see if it can be discovered and how it is discovered. I think I'm running out of paper. I should have brought some more paper. Anybody have? Okay, no, I have enough. Okay, this is the kind of question you might get. Might get the following question. This frame was received. I hope I got it right. 011, 01, 00, 111, yeah. This frame was received, which was coded by Hamming code, using the odd parity system, odd. Does it have any errors? Well, we have to check each group. Right, so I'm gonna just mark them here, the positions on top of this for now, quicker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's better to put them in a table, but for now, actually it's better to go on a table. It's easier for everyone to see. And easier to work out and no mistakes. Right, we're gonna have 4 rows. This is for parity 1, parity 2, parity 4, and parity 8. Right, I'm gonna write those values, 0s and 1s down here in front of parity 1. But you're gonna tell me which positions. Can you tell me which positions that I should write here that make up parity group P1? Where do I start? Do we start with this bit? With which value do we start for P1? We start at position 1, we take it, right? And then we skip number 2 and we take number 3. So just give me the position I should take. 3. 5. 7. Yeah. 9. Perfect. And 11. Now we count them. 1, 2, 3. That's odd. That's perfect. There's nothing wrong here. Who's going to give me the, yeah, give him an elbow, please, there. Yo, are you asleep? Okay, oh, okay, somebody else. Yeah, one, your turn. Group number 2, where do we start? And number 2, so I'll take this, how, right? Take this and 3.
Yes, and then skip 4 and 5.
Skip 4 and 5.
Take 6 and 7. 9, take 10, 11.
And count 1, 2, 3. That's another odd. Perfect. P4. Okay. 4, 5, 6, and 7. And skip the next 4, 8, 9, 10, 11, and that's it. And that's 1, which is an odd number, which is perfect. Okay, who's gonna take the last one? We give you the easiest one always, don't we? Okay, number 8, P8. Where do I start? At number 2 or 3?
Right.
8. Right, so that's 1.
9, 10.
That's it. Okay. And no more. So we stop, and there are 3, and that's odd, and they're all correct, and therefore there's no error in the frame. So that's how quick. You do it a couple of times and you fly through it, but it's good to know. Now, again, I'm gonna do the same trick, guys. I'm gonna right, so it's 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0. Now, this is the frame received using Hamming code. This is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And again, it's good to have those. You know, I have no idea that if you have square kind of paper, it will work much easier, or if you create a table. It's much, much easier, because you can get mixed up so quickly, so easily with these bits in the wrong column, and you count the wrong one. Now, P1, P2, P4, and don't go P3 here, be careful, and P8. Now, P1, please. 0? Just call me the numbers and I'll do the copying.
Okay, yeah.
Position 1?
Yeah, 1.
And 3?
No, sorry, 2, 4.
This is P1.
Oh, P1, sorry.
You start at 1,
3.
you take it,
Yeah.
skip, yeah, 3.
3, take it, 5, 7, 9, 11.
How many? 2. Oh, there is an error. There's an error in P1. Right. Next person. P2.
2, 3.
2 and 3.
Yes, 4, 5, then 6, 7.
6, 7.
And 10 and 11.
Skip 8 and 9.
Yeah, then 10 and 11.
And take 10 and 11. And how many are there?
3. So that's it.
Odd. That's okay, but this one is not okay. P4. You need takers. Go on.
4, 5, 6.
4, 5, 6, 0, 1, 0, 0. 7. And the rest. And it's 1. And it's odd. And it's perfect. All right. Next one. Who wants to take the 8? You're always take. No, go on. Take the 8. 1, 0, 1, 0. And it's 2. It's even. And it's a problem. Right? Now, there's a problem in P1 and a problem in P8. If you add these two, it will tell you the bit position. If you had problem in 1, 2, and 8, it's 1 plus 2 plus 8, position 11. If you had a problem in 1 and P4, it'll be 1 plus 4, it'll be bit position 5. And if in reality, that's exactly the bit I changed, number 9. See, number 9 was a 1, and I turned it into a 0, and that's how simple it is in Hamming code. How simple it is to discover it once you apply the algorithm. Okay, you find out which parity bits that have the error. Forget about the 2, 1 here. Some students, they start adding 2 plus 2 plus. That's not it. Which parity bit had a problem? P1 and P8. So you add 1 plus 8. If you had problem with 1, 2, and 4. You add 1 plus 2 plus 4, and that's bit 7. Right? Okay. Okay, this time we're going to switch to even parity bit Hamming code. I'm going to give you some data. I say send this data. You apply Hamming code to it. Generate Hamming code. That means generate the data and the parity together according to Hamming code. And show me the frame to transmit. Okay, so your data, I'm going to send is this one here. This is the data. Can you please generate Hamming code for this data? So usually you should have a table or positioning system for position 1, 2, 3, 4, 5, 6, 7. Define which ones are the parity and where do you put your data. So this is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Now, where do you put your data here? First thing you decide where to place the data and then work out what's the P1, what value P1 is going to have, P2, P4, and P8. That's not me, I hope, is that? Do I? Right. You have 5 minutes to do it. Well, 4 minutes. While I enjoy myself with a cup of tea. If you don't know how to start, let me know. And I don't have any more papers. I might have. Anybody needs a paper? No? No? What position are the parity bits? Where did you place your parity bits? What? It's even, guys. Well, if you've done it all, okay, but let's go for even. We're working on even Hamming code. You done? Your data to transfer? Not yet. Okay. Yeah, it's same as everything else. Okay, I'm gonna go through it. And this is the way you should. And in an exam, that's the way you should show your work. Most likely, in an exam, I'll be given marks for each one of those, for each line, especially for the receiver part, like two marks for this correct one. You might get some parts, these two wrong, at least you get 2 marks for one of them. But if I see it, you get some marks. And then the final byte or the final frame that gets sent, make sure, you will be asked to write it. If you don't write it, you don't get the mark for it. Okay, let's see how it's done. First thing, this bit location and that, they are the parity bits. We don't put data in those. 1, 2, 4, 8. Reserve those, don't touch them. Now, let's put the data. So that this data goes in there, that one goes there, the second one goes there, this is the third one, and the fourth one there. Yeah. And then double zeros and a 1. Now, let's work out the parity bit. The first parity bit, how do we work it out? We take this position, we skip this, we take this one, number 3, we skip 4, we take 5, skip 6, take 7, 9, and 11. And we count them, 1, 2, 3, 4, they're already even, 4. So, and therefore the parity is gonna be a 0. Position number 2, we go to parity bit 2, we go to location 2, we don't know what value, we take 2 and 3, we skip 4 and 5, we skip 2, and we take 6 and 7, that's 1, 1, 1, we skip 8 and 9, 10 and 11 is 0, 1, that's it. How many bits? 1, 2, 3, 4, that's another 4, that means the parity bit P4 is 0 as well. Where is it? No, sorry, that's parity 2. What am I talking about? Yeah. No, that's another 0. P4, starting at location 4, we take 5, 6, and 7. That's 4 bits, and we skip 1, 2, 3, 4, and that's it. We have 3 odd, that means the parity has to be 1 to make it even. And therefore, this is 1. The last one, 8, we go to location 8, we take 8, we take 8 and 9, 10 and 11. That's odd, that means the parity has to be a 1 to make it even. So this is 1, and this is the actual final data that gets sent. I should write it here. So it's 0, 0, 1, 1, 1, 1. 6 ones, is it? 1, 2, 3, 4, 5, 6 ones, 2 zeros and a 1. If you got it that way, this is the way it should be done. So now you should write the final marker. Now, I'm gonna flip one of the bits here, and you should do what the receiver should do. So, okay, so I shouldn't tell you which bit I'm gonna flip, so look away guys, but it's 0, 0. Okay. Okay, 2, 4, 6, 1, 2, 3, 4, 5, 6. I'll mark it just stronger there so you can see it. I don't know if you can see it. 0, 0, 1, 2, 3, 4, 5, 6. And then I'm gonna go 0, 0, 0. So that's the data. No, sorry. I'll put this back as 1, sorry, my apologies, the last one. It's this one here, 1, 0, 0. So it's 1, 2, 3, 4, 5, 6. I'm gonna turn this into a 0, 7, 8, 9, 10, 11. There you are. Please take it from there and find out which one has the error as we went. The point about it, the way you should do it, you should work out each parity. Parity 1, find out if it has an error. Parity 2, parity 4, and parity 8. And if none of them has an error, then the data has no errors. If any of them has an error, add their values, 1 plus 2 plus 4 plus 8. And that should tell you which bit, the position of the bit with the error. I'll do the first one for you. Start at number 1 and take 1. Skip 1 and go take 1. Skip 4, take 5. Skip 6, take 7. Skip 8, take 9. Skip 10, take 11. And this one has 1, 2, 3. It should be even, but this one is 3. There's a problem with parity 1. That's how it works. Now try check 2, parity 2, parity 4, and parity 8. I could be wrong, but I don't think so. You know, correct me if I'm wrong, guys. Okay, correct. Once you discover the problem, write me the new frame. Remove the bit and then remove also the parity. Just write me the data. Okay? So we got to do that thing. First one has a second. Maybe it could be, maybe you're right. Second one, you should have taken 2. 0, 1, okay. And then you skip 1, 1, you took 1, 0. And then you skip 1, 0, and out. What's finished? Yeah. That's these are the parties, which these ones are right. And then remove the parity bits and just write me the data. Okay?
Yeah, so remove it and I
Which bit? Okay, so you flip it and write the frame. And then get rid of the parity bits and just write me the user data. Where are the parity bits? It's position 1, 2, 4, and 8. Get rid of them and you're left with the data. Okay? So, yeah, you write it here. You write in the exam, leave it there, and then write the new data there after flipping. And, okay? Which bit? So you write the new data with the changes, and then that's good. And then get rid of the parity bits and just write the user data without the parity. So the parity was something that was added by the center. That's not the original user data. Get rid of the parity 1, 2, 4, 8. Just write the rest of the bits and that will be all. Oh, yeah.
yeah.
Okay, guys? Right, we work out each parity bit. I've already done P1, but let's go through it again. You say P1, go to place number 1, position 1, take 1 bit, skip 1, so we skip number 2, we take the value for the 3rd position, we skip number 4, we take 1 for the 5th position, and then we go to 7, that's a 0, we go to 9, that's a 0, 11, and that's a 1. And we count. How many ones are there? 3. They should be even. That means there is a problem in P1. Now let's go to number 2. I start at position 2, so we start at this location. And we take 2. We take the 0 and the 1. That's 2 and 3. We skip 4 and 5. Take 6 and 7. 1, 0. We skip 8 and 9. And we go 10 and 11. And we see how many bits are there. 1, 2, 3. That's another odd. That's another problem. So we go to the P4, the parity 4. We go to start at location 4, which is this location here. We take 4 bits. That's 1, 2, 3, 4. From 4 to 7. That's 1, 1, 1, 0. And then we skip 4. 1, 2, 3, 4. And then if there were more, we'll take more. Now, there's also another 3, which is another issue. So it must be one of those bits that's common to parity group 1, parity 2, and 4. And these, so I bet you P8, I don't know, we'll see. Now let's go to P8. P8, we go straight to number 8. We take 8, so we take 1, 0, 0, 1. As you can see, P8 is not involved in bit 7 at all. That's not one of its group. So if the bit that has all the bits that have errors, what is the common bit between them? As you can see here, for example, if we got an error in bit 1, that's only common between group 1 and 2. So if only group 1 and 2 are wrong, you'll find that most likely group bit number 3. If you had 1 and 2, that's bit 3. And as you can see, these two here bits are the common. Bit 5 is common to group 1 and group 4. Like from the table, you can see which groups or which bits are common to which groups. I don't know if you can spot it, but it should be quite clear. Now, let's finish this. P8 has a 2, which is an even number, which is okay. So now we have problem with P1, P2, and P4. That's 1 plus 2 plus 4. This is the 1, 2, and 4, not those here that are written there. But that's the problem, the group problems. 1 plus 2 plus 4 is 7. And if you actually correct number 7, flip it from 0 to 1, everything else will work correctly. And that's Hamming code. Hamming code is beautiful. It works so perfect for 1-bit error. It's so efficient. And it uses very little, reasonably little bits as, redundant data. And it corrects, it tells you, pinpoints which bit it is. But it's not efficient when there's 2 or 3 bits or 5 bits or 7 bits, it becomes unusable. It's very inefficient then. If we are guaranteed we're only going to get 1 bit error, it will be perfect. But of course, that guarantee is never there. Whenever we get bit errors, we usually get a lot more than 1, generally, so it's not dependable. So it's beautiful, mathematically it's lovely, but only good for 1-bit error. Maybe, there's another algorithm that will do, but otherwise it's fast. It also uses the parity system and counting and, the same as the logical numbering systems. All right, so we have one more error detection system. We'll probably do it next week. Very simple. The sum, we'll talk about it next week. But we've done good bit today. We've done the normal parity system. We've done the block parity system. We've done CRC, and finally the Hamming code. So, just the usual question: which one of those was better? Which one is better, the parity or CRC? It's the man of the moment. Go on. CRC is better. It's a great answer. Why? If you give me a reason, we'll accept the answer. Otherwise, it's the wrong answer.
Or if there's
Is it faster than parity system? Is it faster? What do you think? Parity systems or CRC? They're both fast. They use the logical, operation. So there's very little difference between them in speed from processing point of view. But CRC does not have to wait until it's all done before it can start sending the frame. It can start handling the frame, and the transmitter starts behind it transmitting, and it's calculating. And by the time it finishes, the last, remainder, it leaves it in memory, and the transmitter will transmit it. So it's so fast, and it doesn't have to wait until all the work is done before the transmitter can start sending the data. So CRC might be a little bit faster if you put it that way. Okay, which one has more redundant data? CRC or parity systems? Parity systems has more. What's the parity, what's the redundant data in parity systems? How much redundant data in parity systems? Say again? 1 in 7. Well, 1 to 7. A ratio of 1 to 7 or 1 in 8. Every 8 bits, one of them is redundant. Every 8 kilobits or kilobytes, 1 kilobyte is redundant. So it's a 1 in 8 or ratio of 1 to 7. That's very, very high rate. How much redundant data goes in CRC? 1 or 2 bytes at the very end of every packet for the full packet. Right, so it's much more efficient from this point of view. What else? What errors cannot or can be discovered by parity systems? What errors cannot be discovered by parity systems? I come back to you. Parity system, the first system we talked about. Any idea?
Uneven number of beats are flipped.
If an even number of bits flip, yeah, I nearly said wrong answer. Yeah. I wanted to say wrong answer. In a byte, in 1 byte, if 2 bits or 4 bits or 6 or 8 bits flip, they cannot be discovered. If they're in separate bytes, they would be discovered, so be careful. Right, and what errors can be discovered in CRC? Give me one group of errors that will definitely be discovered by CRC. Any odd number of bits, 1, 77, 13, all these bits in one frame will be discovered for one packet. Any other group that will definitely be discovered? If the number of bits that flipped or that are involved in the error are less than the length of the generator. The generator usually 15, 16. That's the standard number of bits that are used. Right, and what is finally what's this binary representation of this polynomial number?
1, 0, 0, 0, 1.
Perfect. Thank you, guys. It couldn't have been better. I'll see you next week.